In this lesson, we're going to present and compare the four fundamental forces of nature. Okay, so the first fundamental force is the one that you've already come across, which is the force of gravity. This is the force that acts between masses, okay, and it is an attractive force only. And gravity is the force that, for example, pulls an apple to the ground. It's what gives us weight, and it is also the same force that pulls the moon around the Earth in its orbit and the planets around the sun in their orbits. Okay, so we're going to be looking at gravity in a lot more detail in a later lesson. This is just a brief review and comparison of the forces. So the next fundamental force is the electromagnetic force, and that can be divided into, if you like, two forces. First of all, the electrostatic force. That's the force that exists between charges that are stationary. And remember that those charges can be either positive or negative. And so if we have two positive charges together, that will produce a repelling force, or two negative charges. Or if the charges are opposite, positive and negative, then that will produce an attractive force. Now, so this is the electrostatic. That means static means not moving. That's the force produced when these charges are stationary, but when these charges move, they produce a force called the magnetic force. Okay, and so the magnetic force is produced between moving charges. Again, we'll look at this in much more detail when we look at magnetism. And as you already know, we can talk about a repelling force if we have a north pole and a north pole together, or a south pole and south pole, or it could be an attracting force if we have a north and south pole together. Okay, so both the electrostatic and the magnetic force can be either repelling or attractive, and these two combine together to form what we call the electromagnetic force. So that is the second fundamental force. Now, the third fundamental force is the nuclear force. Now, the nuclear forces originate in the nucleus of atoms, for example, and they can be classed in themselves into two fundamental forces. One is what we call the weak nuclear, and the weak nuclear is responsible for radioactive beta particle emission, which we'll look at when we look at radioactivity. So here we have a neutron, that's the brown dot there, which is decaying into a proton and emitting a beta particle. So this weak nuclear force is related to this beta particle emission. And then the strong nuclear force is the force that exists between nucleons in the nucleus. So that's the force that holds the protons and neutrons together, or the neutrons and neutrons together, and protons together in the nucleus. Okay, so let's just compare more qualitatively, really, these three fundamental forces: gravity, electromagnetic, and the nuclear force. We'll deal really here with the strong nuclear force. And first of all, what we can say about gravity is that it's a very weak force, whereas in comparison, the electromagnetic force is much, much stronger. So to give you some sort of idea, imagine a hydrogen atom where you've got a single proton and an electron whizzing around in its orbit. Well, first of all, both the proton and the electron have a mass, so there will be a gravitational force exerted between these two particles. At the same time, because they are both charged, the proton has a positive charge and a negative charge, there will also be an electromagnetic force interaction between them. And so if you compare the size of the two interactions in this single atom, you'll find that the electromagnetic force is approximately 10 to the 39 times stronger than the gravitational force. So that gives you a rough idea of how much stronger electromagnetism is compared to gravity. So, the only reason why that we're really aware of gravity at all is because the object on which we are all sitting at the moment, or standing, is absolutely enormous, that is the Earth. And so we are aware of this force acting on us, causing us to have a weight. Now, comparing the nuclear to the electromagnetic force, well, it's roughly 100 times stronger. So we would say we've got very weak, they're much stronger than, even stronger for the nuclear force. Well, what about the ranges of these forces? Well, the range of the gravitational force would be classed as a long-range force, although it depends upon the mass of the object that's generating the gravitational field. So, for example, the gravitational field produced by the Earth has much less range than the gravitational field produced by the Sun, which would have much less range, for example, than the gravitational field that is produced between galaxies. So, here we would be talking about a very long range force, whereas, for example, the electromagnetic force would be classed as a short range or shorter range force. So in a similar way that the range of the gravitational force depends on the mass of the object that's generating the gravitational field, in magnetism, for example, the range of the magnetic force depends on the size of the magnet that's generating the magnetic field. So, for example, the magnetic field produced by a couple of standard laboratory bar magnets might have a range of, say, 10 or 20 centimeters, whereas the range of the magnetic field produced by the Earth, well, that might extend to 3 or 4 Earth diameters into space. But that would still be classed as a short range force compared with gravity, whereas the nuclear force would be classed as a very, very short range force. So, for example, this is a force which acts within the diameter of the nucleus of an atom. So you're talking about a range of less than 10 to the minus 14 meters.